Welcome to our fourth plenary session of this USNCCM. It's my singular pleasure today to introduce Nathan Kutz. Nathan is the Robert Bowles and Yasuko Endo Professor of Applied Mathematics at University of Washington. Nathan's interests in applied mathematics and computation really span the field pretty much. He's described largely as a computational scientist, but of course in this forum we need to be more specific. I tend to think of him as a dynamical systems expert and tends to look at things from that viewpoint, according to me. And Nathan may correct that in a second if he likes. But really, he's looked at problems where dynamical systems show up in physics, right? Fluids, solids, materials, all kinds of other linear and nonlinear phenomena, neuroscience, reaction diffusion systems relevant to cell signaling, even Bose-Einstein condensation, as I see. From methods, I mean, everything that one really needs for these kinds of problems, right? Variational methods, numerical methods, of course, all of applied mathematics and so on. Nathan's won many awards, of course, and I suspect I'm reading from a very incomplete list, but I'm going to mention a few of them. Fellow of the Radcliffe Institute of Advanced Studies at Harvard a few years ago, a number of best paper awards, all kinds of the usual agency awards and visiting professorships across the world and so on. What I'd like to say is that Nathan's work has become really significant and relevant and sort of topical and is driving the conversation, I should say, in the last few years, because he's been looking and he looks at data-driven modeling, but not just the data science aspect of it, but it's all entirely physics and fundamental principle driven. And you can see that from the title of his talk today as well. And along the way, he has been asking the kinds of questions that have occupied his mind have been the sort that have actually driven a lot of the fundamental development in mechanics itself, right? Questions of coordinates and the relevant operators to describe things and so on. Anyway, okay, I'm talking too much, so you really are here to listen to Nathan, and that's what I'll let you do now. All yours, Nathan.
Thank you so much, Krishna. Hi, everyone. I wish I could be there in person. We were just, Krishna and I were just talking about how nice it will be when we finally get to be back together again in person. And it'd be nice to be in Chicago where I did my graduate work. So I'm going to be talking about, you see the title there, it's sort of data-driven model and really towards trying to pin it back towards what we think about as our standard physics modeling paradigms. This work is in collaboration with Steve Brunton. He's one of my main colleagues, and really what the work is going to feature is the work of these fantastic group of students and postdocs that we have interacted with over the last few years in trying to build these physics-informed learning paradigms, using emerging machine learning methods on dynamical systems. So Krishna had it right. I love dynamical systems. And now we have a new tool to play around with to learn some things from data. So my start point is going to be, for this conference, fairly relevant. Here it is. Everybody took a class in statics and dynamics, right? So in fact, I bet you, I was just thinking about this. I imagine, when I took statics and dynamics, I even remember the classmates I had that I took statics and dynamics with, because we were working through all these problem sets. And I'm just giving you one representative picture of what a statics and dynamics book looked like. And there it is. All of you remember this probably. And this is out of a page out of Rena's Pratap's book. So let's talk about how we solve these problems. Typically, the big thing here was you knew that the sum of forces was either equal to 0 or the sum of the forces was equal to MA. And so all you really had to do, now I say that in air quotes, was essentially draw the correct free body diagram or find the right coordinate system in which to represent this. And so one way to think about everything I'm going to talk about today is this, but now in the context of machine learning, where essentially the idea is to use the machine learning agents to help us represent the physics in the right coordinate system, because if you didn't represent this in the right coordinate system, it's a very challenging problem. But once you got the right coordinate system, and the governing equations together, then you could get the solution worked out pretty nicely. And by the way, this kind of concept is pretty old, and so I'll highlight some of it more as we go along, but the idea is here, encapsulated in hopefully one figure that I want to keep coming back to over and over again, which is from data, which is really represented here on the left side, our input data stream. Can we use some methodology? And of course, I've already put in a neural network architecture here because it's already going to foreshadow what we want to actually do here, to learn a coordinate system where in that coordinate system, I get down to a representation of the dynamics of that problem, and then I come back out. Now, what I want to do is think about this as a targeted use of neural nets, because I want to be able to interpret the various pieces. In particular, once I get into this space in the middle where the dynamics are represented, I would like for this thing to build for me a model that has, in fact, a lot of interpretability for the problem I'm looking at, okay? And there's a lot of different ways we've built in these coordinate transformations. In fact, there's classic methods that we've built up, things like Fourier transform your data. It's a new coordinate system, often advantageous for different applications that you might do. So let me give you the classic example that I think will highlight some of this. So in other words, what do I mean by finding a good coordinate system? Because that's one, this is sort of a subjective statement. So I want to try to figure out with you guys a little bit more of what I mean by this. So here's what I want to represent. And here what you're looking at is the retrograde motion of Saturn and Mars. So Mars is up here in the foreground and Saturn is in the background. And this is sort of in some sense one of the oldest physics problems that we really dedicated our effort to as a group, as a species, to understand what was the fundamental mechanisms dictating this behavior. And the first successful theory of this was what's called the doctrine of the perfect circle out of Alexandria, Egypt, in 2nd century AD. Claudius Ptolemy basically constructed a system, an Earth-centric system, where all the motions of the planets could be thought of as circles on circles. And in fact, you could refine those circles, so it's circles on circles on circles, and you could actually have a very nice predictive model for the planetary motion. And in fact, what's interesting about it is one way to think about what Ptolemy did is he produced the first Fourier transform, right? It was a representation as a bunch of circles with different frequencies, add them together, and you can represent the planetary motion as observed from Earth. So this theory was quite accurate, and it lasted for a millennia and a half. And what ended up happening is the world changed. The world changed because observations by Galileo with his telescope, Copernicus with his suggestion of a heliocentric world, what we started to understand is that the retrograde motion was nothing more than the fact that there was an observational, you were basically observing this in the wrong coordinate system, one way to think about it. I mean, we could still write down a model for this, but what Kepler and Galileo really did is establish that actually, if we move to a heliocentric world or planetary system, then in fact, everything falls out pretty nicely as just elliptical orbits, right? These are this big contribution to celestial mechanics that came out of the 1600s. And then what's interesting about this in terms of the context of physics discovery is once you have that correct coordinate system, then this is where Newton can come in with his new developments of F equals ma and basically write down our inverse square law and write down the planetary motion laws. So that was a huge step in sort of the scientific revolution taking off. And really, this is one of the fundamental problems that was sort of in some sense solved at that point. And of course, we know we didn't solve it. In the early 1900s, there were some discrepancies between the data and the model. And this is really fascinating, right? So that wasn't observed before, but once we got good enough observations, there was a realization that something wasn't quite right. There was initially a thought that we were missing a planet, but in fact, that wasn't the case. The fact was that we had, in fact, more physics that was beyond our range of measurement, which we could finally measure, which was general relativity. I put a box to the right of Einstein there, by the way. Because somebody eventually is going to come along, and as we get better and better measurements, they're going to say, well, Einstein was mostly right, but there's some missing physics, and here it is. And the only way we're going to get to it is when we have better and better measurements. And this is kind of an interesting paradigm for us thinking about data-driven science. As we improve our quality of measurements, we go from, and really Kepler, the reason he was able to advance this idea so far was because he had Tycho Brahe's data, which was an order of magnitude more accurate than anything that previously been taken. So there's this evolution of better data, better models, better data, better models. And I think that will continue indefinitely for us, I think, as we build towards the future. So here's the idea in the context of what I proposed. You take measurements from the Earth and you observe the planetary motions, okay? And the idea is to use that neural net or this coordinate discover paradigm to understand that actually there's a better representation of this. In this representation, when you use a heliocentric universe, then all the planets are just very simply parametrized by an ellipse. And then once you have that, you can actually then discover dynamics by having this inverse square law. So I always think of this as sort of the discovery paradigm, what we're pushing for in this. And also it reflects a fundamental belief on my part, and many, I think, of yours and others, that governing equations really matter. And we still want to have governing equations because there's so much we have learned historically from it. And we are in this interesting state where when we have some of these modern machine learning tools, there is a question that what is the role now of governing equations? Because I can simply do end-to-end learning with neural nets. But really, I always think about governing equations as teaching us a lot about the underlying physics that's there. And this is sort of this process we want to get after. I'm going to give you one other example here, which is we built this here at the University of Washington. I mean, it's not a fancy thing to build. We drill a hole in a wall and put a pendulum in there. The point about this video, though, is, okay, if my data that I'm collecting here is just a video of physics, so I'm giving you just the raw video, and I want you to use this discovery paradigm, then what you really should be discovering in that first layer is that from the video, I would discover that there is, in fact, a pendulum and with some coordinate system, theta, theta, dot. I didn't tell it that. That's what it would discover from the data. And once you can discover that, then in that final layer, you can discover the laws of the motion for the pendulum. In fact, that's sort of where I'll end with this, right? Which is, I always think of this as sort of like GoPro physics. You film physics, and from that film, can you extract out governing equations, principles, coordinate systems? And that's what we really want to head towards in our engineering design, especially as we're getting amazing sensors that we can use in almost any kind of context. I want to come back, though, to Kepler and Newton. In some sense, this is their contributions are really interesting, because if you look at F equals ma, the solutions for the planetary motions are these ellipses, same ellipses that Kepler had. So why do we always, in some sense, think that Newton was essentially the greater physicist? Partly with F equals ma, I think the real concept here is Kepler was able to regress and fit to these parabolas, so he had a great model for it. But with F equals ma, you can do the following. You can do an extrapolation. So Kepler did an interpolation. F equals ma allows you to do an extrapolation. Here's an extrapolation we did in the 60s. We extrapolated, said if I launch a rocket from the Earth, you could put it in orbit around the moon. I've never seen data with that. Yet we had the governing equations allowing us to plan that trajectory and how to bring the astronauts back to Earth, right? So this is the power of having governing equations, is the capability to imagine new regimes and to extrapolate into areas where I've never collected data, right? So that's one of the limitations, obviously, that we have with modern neural networks, for instance, that everybody's using, is that they're interpolatory devices, and we always have to keep that in mind. All right, so where is this reflected in the modern world? Well, I like to show these two here, which are two examples of autonomy, right? So this is, in my view, sort of Kepler and Newton in 2020. Like, what is the this tension between model building in Newton way or Kepler way. And these two are amazing technologies. They are, in fact, in many ways, they are sort of the big challenge problems of our day. And what's interesting is they work on very different principles. They're both data driven. They're both autonomy, but the top one is completely imbued with physics. So in other words, that robot has understandings of F equals ma. It knows its masses. It knows the length of its limbs. It has a physics engine underneath it in order for it to carry out its tasks. Whereas the car has a bank of sensors, no physics. It just simply, rules. So some deep learning agent which says, here's your acceleration pattern you should use, your braking pattern, label the earth, the landscape around it. It inherently doesn't have any knowledge of F equals ma. Both paradigms are very successful. The top one is interpretable. The second one, the bottom one, the car, is maybe not as interpretable, although again, interpretable is very subjective term, right? So what I mean by interpretable, especially for the top, is I know the physics principles underneath of why that would be working, right? So it's, it's angular momentum. Concepts like this would show up in this, whereas with the car, it's convolutional neural nets, deconstructing images, making labels. Once you label it, you avoid things. Drive on the road, not the sidewalk, which gets labeled in some image classifiers. Okay, so I'm going to spend most of my time thinking about the top. That's where I want to live. And by the way, whatever this is, everybody's going to have their view about how we go about this from machine learning in the future. But this is just one perspective. It doesn't mean I'm right or it doesn't mean I'm wrong. It just, there's plenty of methods that are going to be developed all around us for doing different engineering problems. So let's talk about the mathematical formulation then. This is the mathematical framework that really helps us couch, I think, the whole physics-driven discovery here, which is I have measurements of a system. And the measurements are different at distinct time points, T of k. And so my measurement vector is y here, but I don't necessarily know even what my state space is. So for instance, when I took the video of the pendulum, the point is I'm not necessarily telling this system, oh, there's a pendulum in there, here it is, I label it. This is just something it would have to discover. What is the underlying state space through some measurement model, which often has noise on it. And then the dynamics is given by some dynamical system here. Let's say dx equals some f. So f prescribes our governing equations. And typically it's parametrized. So oftentimes, these nonlinear dynamical systems can undergo bifurcations or instabilities. So this is sort of our generic framework from measurements alone. So this is the goal. I give you just measurements. Your goal is to tell me what the state space is, prescribe the governing equations and its parameters, and also even tell me the measurement model. So this is a terribly ill-posed problem. Like, you don't have enough information to do this. And so back in grad school, since I showed you the picture of statics and dynamics from undergrad, in grad school, if that was the first time I learned about ill-posed problems. And normally what I learned about it is if you see someone says this is an ill-posed problem, you go do something else, right? Because it doesn't have a solution. And now what I've learned with machine learning and sort of this more of getting into data-driven models is, oh, there's no problem. If it's still posed, then all you have to do is impose some constraints or regularizations on this mathematical framework, and then you can make it well-posed. And that's exactly what we're going to do here. So the question is, what kind of constraints do I want to impose here to make this well-posed? So the constraint I'm going to put in here is one that I think is common for us who do a lot of engineering and physics type systems, which is the idea of parsimony interpretability. What do I mean by that? So what I really mean by that is if you look behind me, right, I have a bookshelf and I have many learned books of physics and engineering, and I can pick any of them up. But think about it. You pick up a fluids book and here's Navier-Stokes and it's got, 3 terms, and Maxwell's equations, not many terms. Schrodinger equation, not many terms. So what I mean by parsimony is, if you look at the advancements we've made, governing equations are this really powerful, compact engine for doing science. And so our books here are full of equations of motion that we have studied and make significant technological advancements with, and they can be represented in these very parsimonious ways, right? Think about like how much dynamics comes just out of Navier-Stokes. It's amazing, right? You can get all kinds of interesting fluid dynamics, and especially as you go to high Reynolds number where we get turbulence, we still don't really understand that as well as we should, or it's very difficult for us to characterize turbulence in quantitative ways. So what I mean by that is, not only do I have the interpretability because of those models, because I know what a diffusion term does, I know what dispersion does, but we also have this compact representation. And these ideas are very old, right? William of Ockham was one of the first to really start talking about nominal models, nominal representations. And he was really pushing back at that time in the 1200s on sort of people getting carried away with Aristotelian logic, where they were building these really large constructs. And William Ockham said, look, build the nominal representation of things. Pareto as well, later in the 1900s, really started advocating. And so Pareto I highlight here because we also have this idea of the Pareto front, the Pareto frontier solutions. And again, that's all about trying to find a nominal model that does a good job in modeling the data, but it's not over-parametrized. So that's what we're going to go after. And by the way, there is a question of why would you believe any of this would work? And I think my answer to that, right, is like, if we go into the modern day and it's like, why do you think, why am I strapping myself to an old idea? I've been actually, not quite to my face, but I know people have thought, that guy's a dinosaur, he's still sticking with his governing equations. But the reason I believe that still makes sense is that if for many of us who believe in dominant balance physics, in other words, when you measure systems and you see that the emergent phenomena that comes out, that's usually coming not because you've got this incredible model, it's just there's a few dominant balance terms, and that's what you really want to represent when you build a model, right? So that's why I believe governing equations still play a huge role in terms of our future of modeling systems. Okay, so let's talk about what we might do here. Remember, I'm going to try to pair a coordinate with a model. And at first, what I'm going to try to say is, hey, here's a really simple model, a linear model. What if I found a coordinate system in which the dynamics is linear? And this really goes to this idea of Koopman representations, or Koopman theory, that you may have heard of. And so what we want to do is just simply say, well, maybe there's a coordinate system, this all works really nicely. And in fact, what I'm showing you here is a very simple example, but it kind of highlights a lot of the main ideas. So on the top left, over here, you see this governing simple 2x2 nonlinear differential equation system. But if I write it in terms of this coordinate system here, y1, y2, y3, which is x1, x2, x1 squared, then this thing becomes completely linear. So this is the idea. You move from your original coordinates to a new coordinate system where everything's linear. And so really this is this vision of Koopman that it was proposed in the 30s that was brought back up, where we finally had some algorithms for doing this, from Peter Schmidt in 2010, the dynamic mode decomposition, which Rowley, Mezich, and others showed that in fact the DMD was a way to compute an approximation to the Koopman operator, and we've just been building on that since. And this is what's great about linear models, right, is they're easy to solve. So so we can use all of our standard techniques, out of differential equations to write down decompositions. But what we're going to do is, instead of we're going to start using neural nets for this process of this discovery, right? So if we have this concept where I can move from my original coordinates to a new coordinate where it's linear, I want to use neural nets to do this. And this is just a reminder. This is from a quote from Stefan Malat. It's the first sentence of his book, of his paper on understanding deep convolutional neural nets. It's supervised learning is a high dimensional interpolation problem. That word interpolation is so critical, right? So that's what really neural nets are doing. Now we're going to take some data, we're going to train this. So you have to have a really great data set, because the neural net's only going to allow you to really sort of build an interpolation engine. So here's the idea. We're going to actually go back to a pendulum problem just to see if we could make this happen. The pendulum itself is only linear for small oscillations, but of course the pendulum really is theta double dot is equal to minus sine theta, right? So that's with no damping. So it's really a nonlinear differential equation. And the question is, well, that's probably one of the easiest nonlinear differential equations. Let's see if we could do it. And so this is with work with Bethany Lush. She's at Argonne National Labs now. But what Bethany did is she started to say, let's make a transformation, just like I showed you earlier, right? So you start with your input space. You're going to learn a transformation to a new coordinate y, and then come back out to the original variable. And what you want to have happen in this new space, again, I want a coordinate transformation to this new variable. And in this new variable, when I go from y of k to y of k plus 1, in other words, take a step forward in time, I want that to be a linear map. And that's the Koopman operator. So, and if I want to take multiple steps forward in time, I just take this linear mapping or this linear operator k and just lift it to some whatever power the number of steps is. So this seems like a very easy concept, right? Let's train this thing. So I just build a linear model in the middle. Of course, nothing's as easy as it seems. And one of the reasons is, and by the way, also, I want to do this and retain this to be 2 dimensions, right? So I know that the pendulum is sort of 2-dimensional, it's theta, theta dot. And I could really collapse it down to just its angle, action angle variables if I wanted to. But it, like, you know, there's a very low dimensional representation of the pendulum in this coordinate system. So I could, of course, just go to high dimensions, but I really want to keep my interpretability, keep it to 2 dimensions. But by doing so, there is a problem. Specifically, when you look at the pendulum, here is a spectrogram of the pendulum. In other words, as the amplitude gets bigger along the x-axis, and I'm showing you the frequency content along the y. So what you're seeing here is, here's the main frequency. As the thing gets more and more nonlinear, the frequency shifts and you produce harmonics. In fact, we've known this forever from perturbation theory. That's what nonlinearity does. It shifts the frequencies, creates harmonics. So you have to account for that. So we change the neural network slightly is to parametrize this linear operator by the frequency. So you can keep this thing 2-dimensional, but now you have a parametrization of that frequency. And so in doing so, you can completely linearize that pendulum. So you can take it, make a transformation, move yourself into a coordinate system where these nonlinear oscillations, which get to be strongly nonlinear, you can warp them into linear, into a space where it's all linear. And here's the coordinate transformation. This is sort of these are sort of your coordinates that you transform to, a representation there with the neural net, that what it found. So this is nice. You essentially linearize the pendulum all the way up to the saddle at the top. We did a little harder problem, flow around the cylinder. Again, this is where you get von Karman vortex shedding off the back end. And this is it's been shown to be some nonlinear dynamical system here, very much like a Hopf bifurcation that happens back there. It's not quite a Hopf, but it's Hopf-like. We took this flow around the cylinder and again did the same thing. Can we learn a transformation to make the flow around the cylinder linear? And in fact, we can do that by learning this coordinate transformation. So this is a powerful idea. It can be fairly restrictive. I'll talk about that later, but it's also in many problems can be really nice to have this linear operator that tells you everything about the physics in the right coordinate system. In fact, we did a much harder example here, and this is work with Craig Jin. So Craig followed up with Bethany and Steve and I on looking at PDEs and saying, okay, let's take a really hard PDE, something like the Kuramoto-Shibashinsky model, which actually has a lot of spatial temporal chaos, and ask the question, could we in fact embed this in some linear subspace where the dynamics is linear? And I'm still surprised we made this work. So if you have a large training example, I'm not going to pinch down to low dimensions here as much. I'm going to try to make it as parsimonious, as few dimensions as possible, but we can actually learn a transformation, and these encoders and decoders are a little bit more sophisticated than we were working with previously. But basically, given a large set of training trajectories, we can do this for the Kuramoto-Shibashinsky model. We can actually learn a transformation where the dynamics in here is linear. In fact, what you're looking at over here is, here's the exact solution running the full nonlinear Kuramoto-Shibashinsky model, and we just shown some small snapshots of time. And here is what this linear network does. It just reproduces it beautifully. And all the dynamics there is linear in this new coordinate system. So you can do some pretty fancy things with this kind of architecture. You could also just try to warp time series directly. So this is work with Henning-Lange, which is, okay, suppose I have some data and I have, you know, it has some, let's say, periodic, quasi-periodic behavior downstream. So normally persistent behavior has a lot of that kind of behavior. So what we did is instead of say, well, when you build a linear model, right, you're really projecting into exponential behavior, sines and cosines. So that's the fundamental solutions of x dot equals ax, right? They're exponential. So we could say, well, for persistent dynamics, let's go ahead and just build a model that directly projects onto sines and cosines. We could do that right here, or we could take any time series, which, you know, something like this would cost us a ton of sines and cosines. We could learn a neural network that takes time series data or spatial temporal time series data, warps it to make it look as sinusoidal as possible, and then we fit it to sines and cosines. So this is a really powerful concept because it's really exploiting all this amazing structure of Fourier series that we've made so much progress with in our own scientific efforts over many decades. How well does it work? Well, we try to do this for forecasting power grid data. The one thing I want to point out here is this Koopman forecasting method, it really beats all of these sort of state-of-the-art neural network techniques. The reason I think is because you've actually put physics knowledge in, right? I mean, that's really what you've done here. And so it's not surprising that you can build the LSTM, the GRUs, the equistate networks, along with standard statistical forecasting tools. In fact, this thing really does superior performance all around, okay? And so in other words, there's also another message here. Neural nets don't just beat everybody, right? Neural nets, they're great tools, but I think you can, if you set up the right problem with the right kind of priors and the right physics informed pieces, I think you can pretty much beat almost any neural network architecture, which is just throw the data in, give me a model. That's just an opinion, of course. Okay. By the way, you can also use this on spatial temporal data. You could take something like this. This is cavity flow. And what we did here is take snapshots of this, look at the low dimensional embedding. So if you do reduced order modeling, this is what you might do. And you say there's some low dimensional subspace I can represent this in. So what we do is take that low dimensional subspace, look at the time series with that, and then just do this Koopman forecasting trick. So what you're looking at the bottom is this is actually our forecast. It's super stable. It's extremely accurate. And essentially, I'm not even solving anything. I'm just saying what time, you know, put in the time that you want the solution, right? So the solution's already there. So just all I have to do is put in the time. And so it gives you a very nice way and very accurate way and very stable, robust way to do reduced order modeling. Okay, so, you know, I've been talking about linear models, but really nonlinear models is maybe where we might want to go with this, because nonlinear models can capture some of the more interesting phenomena like chaotic dynamics, bifurcations. And so how can we now learn a coordinate system to build a nonlinear model? And this is where we use this idea of SINDy, sparse identification of nonlinear dynamics. So what this is this is just AX equal to B. Okay, it's a massively overdetermined system where the A matrix is a library of potential right-hand side terms. In other words, I have x dot equals f of x. I don't know what f of x is. But f of x, I want to make, it could come from a library of potential right-hand side terms. Where would I get that library? Well, I have one here. I could just go look through my books and look at what kind of terms to show up often in governing equations, build a full library of it. Here I just did polynomials, but you can get, it's only limited by your imagination of what you might put in there. So that's A. That's the A in x equals to B. The B is if I take the time series data and differentiate it. So I have A and B, that's given. And now the only thing I need to find is X, which is essentially the loadings of these library terms. So if you do a backslash or a least square regression, it'll say all the library terms matter. And of course, we know that's probably not true. If you believe in dominant balance physics, you know that maybe only a few of these columns matter. So all I have to do is solve this AX equal to B and promote sparsity. We do this with sequential least square thresholding. So if you take in this data, you take the time series data, differentiate it, and then you do this regression, sparse regression onto a library of terms, you actually pull back out exactly the Lorentz equations. So this is really nice. So it allows you to discover the underlying governing equations. So for instance, here's a table, all these PDEs. If I give you the data, just spatial temporal snapshots, say, here's the data, can you discover the PDE that generated the data? We can just use this architecture. This was done with Sam Rudy. And yeah, here's a bunch of examples of this. Okay, when we first did this, it was not very robust to noise, but we've made a lot of progress on this. In other words, if you start having noisy data measurements, how well does this work? Well, initially we couldn't handle too much noise, but we've worked hard at building methods that allow us now to actually handle much more significant more noise. You can also use this in a UQ Bayesian framework. This is work with Seth Hirsch. And in fact, David Barajas Solano gave a talk, I believe, yesterday exactly on this. So this is just a shout out to David and Seth. But we basically framed this, instead of doing the sparse regression, you can just use a sparse promoting Bayesian prior. And actually, instead of just getting numbers for this regression, you get a PDF for each one of the probability of inclusion for each one of the terms in the library. So the nice thing is, once you get the PDF, not only do you have uncertainty metrics, but you can clearly see a bunch of them are, look like they're mean zero with some variance. And here's some that are clearly non-mean zero. So this can tolerate a significant amount of noise and can handle a very small amount of data. So I'm super excited about this. This just came up on the archive just a month ago or so. So anyway, for those of you who love Bayesian methods, there you are. But by the way, look, most problems we come to, it's not like we didn't know anything about physics, right? I mean, most of us have a book stack behind us as well in your office with all kinds of knowledge. You got your PhD, or you're doing your PhD, and you have a lot of training. So you know a lot of physics. And often when we study problems, there's actually a lot of body of knowledge already there. And so how do we exploit that within the context of this discovery? And so I call this the discrepancy modeling framework, which is, the idea is, instead of just trying to discover a model from scratch, right? What if I start off with, okay, I do know something. I do know this is true, right? So you might have partial physics information. So start there and say, but what am I missing, right? The model I have, and I look at my data, they're just, the model I have is insufficient, and I don't know how to derive the extra terms. It might be too complicated. I can't do it quite from first principles. And so what you can do is say, well, if I know this to be true, notice in this SINDy paradigm, if I know the f of x, I can move it to the left-hand side, and now it's part of the b vector. So I do the same regression, and it's trivial, except for now it has dx dt minus f, and then regress to find the missing library terms. That's it. So it's pretty easy to incorporate, right? So now you're using all your known physics in addition. So where this might be important is systems like this, where if I use my Platonic model, like there's no no frictional forces, nothing, it's very difficult to stabilize this pendulum in upright position. But now you have this cart learn a discrepancy model, and as it starts to learn some of the missing physics that's arising from the resistance, it builds a better model, allowing you to stabilize this in the upright position. Where I think this is especially important is, here we go, the digital twins. Like we're very much into thinking about digital twins. And so here on the left is sort of the twin of the actual robot. And of course, when you build this model, it's a perfect Platonic model, right? I know the masses, I know the arm lengths, but the reality is the real robot has some frictional forces. Each robot probably has different sticking points. And then when you oil them, now it's a different model. From the data collected here, you could take that and build a discrepancy modeling in your digital twin so that this would actually be an accurate representation of this. And so you could use this maybe for precision manufacturing, for instance. You really need to take that step, because the ideal model here simply is not accurate enough to do precision manufacturing. So I think that's where we may come into the future. Some more things to think about. Dynamics and coordinates. So Here, when the SINDy came along, I actually gave you the right state space. You just have to discover the model from the state space measurements. But what we really try to do is say, well, what if I don't actually give you the state space measurements, but in fact, I give you some measurements of it that aren't the state space. So this is work with Kathleen Champion. So what she did is said, okay, I'm going to take whatever measurements you have. So for instance, I give you the video of a pendulum. From the video, this is where I started, right? From the video of the pendulum, learn a coordinate transformation to a new variable set, where in that variable set, I'm going to apply the SINDy architecture. In other words, in the right variable set, I should have a parsimonious description of the physics. And so what this would presumably do is learn from videos of the pendulum, theta, theta dot, and then from theta double, it would learn theta double dot is equal to minus sine theta. In fact, it's exactly what she was able to do. All this code, by the way, everything I've talked about, all the code, all the data you can just download and play with, right? So all the TensorFlow codes for training it, it's all up there on archives and GitHubs. So here we go. So there's various examples. Let me just show you here. This is the nonlinear pendulum. This is like a video of the pendulum swinging back and forth. And basically what it does, it learns that there is a theta theta dot, and then it learns in that variable, there it is. That's the representation of the physics. So we were so pleased to see this. So ahead of time, then you don't have to actually say, I know the coordinate system. This will find it for you, and then it will represent the dynamics for you. So I think it's very promising. And by the way, more broadly within this architecture, there's all kinds of other enforcements that you can make here. So for those of you who love dynamical systems like me, then one could ask the following is, well, if I embed this, could I do more than just learn governing equations? For instance, could I learn normal forms? Normal forms are fantastic because they are these beautiful representation of parametric dependent dynamics. And in fact, there's some very standard normal forms that are out there. So you can actually learn how to embed your physics, especially when you have physics that undergoes a bifurcation, directly into a normal form architecture. You can also do this in terms of looking at periodic solutions. This is work with Jason Bramberger, where you say, I can also look at Poincare maps of the dynamics, periodic flows, quasi-periodic dynamics, and learn deep conjugacies in this. So these are sort of, let's say, more sophisticated dynamical systems terms, but at the end of the day, they are just simply really, this architecture is very flexible in terms of what you might want to learn out of it. Some comments here. The coordinate system is not generalizable, but the idea is that the physics is. So once you learn F equals ma, you can play F equals ma anywhere. It's except just like the statics and dynamics, I have to learn the new coordinate system for it. So the idea is this concept is generalizable, and then for each specific problem, I would have to actually build a new coordinate system. So by the way, just to kind of finish towards the finish here, we can bring in the ideas of how to handle multiscale physics. This is work with Yu-Ying Liu, where you can actually coarse grain and fine grain the physics by sort of learning neural networks that capture, this is very much like multi-grids, right? And exploits transfer learning to say, here's representation of the coarse features, and then you just refine where necessary, right? You say, where am I doing poorly? Refine there with some convolutional windows. Where am I doing poorly? Refine further. So it starts to let you build a multi-scale architecture to help you refine only where necessary and learn multi-scale physics in a nice way. Also, by the way, I've been talking about time-dependent problems, but really you can do this for boundary value problems as easily. And this is work with Dan Shea, who just graduated with his PhD. So you just take this and say, well, I have some input data, and I'm going to try to learn a boundary value problem. So in fact, can you, from data measurements of some boundary value problem, right? So the deformations of a beam and how I'm pushing on it. If I have a bunch of data like this, can I tell you the equations of that beam, for instance, right? And in fact, you can do that. You can use the same SINDy architecture. More than that, you can even build Green's functions. Now, I love Green's functions, at least when I learned them in grad school. And if you notice, Green's functions research, you know, maybe not so much, partly because we've moved into a world where a lot of the physics is nonlinear. So Green's functions inherently rely on linear superposition. And so as soon as you go to a nonlinear problem, this breaks. But what I was telling you earlier applies here to boundary value problems, which is if I can learn a coordinate transformation where this boundary value problem or spatial temporal problem, this PDE, if I can make it linear, I can use my Green's function again. And that's exactly what Dan was able to do. We call this deep green architecture. And so it brings back the full power of the Green's function, which is this fundamental solution to the problem, right? So all I have to do is find that coordinate transformation. And once I have it, I can build that Green's function there. And so now I have, in some sense, the fundamental solution for this nonlinear problem now using this kind of architecture. So I'll end here. So basically, this is the story I've been saying. I believe in governing equations. I believe that we have to start thinking about using some of these amazing neural network architectures in ways that allow us to interpret. I think about parsimony is, if you notice, parsimony for what we did here was the ultimate physics regularizer, right? It was about find me the coordinates to make this very nice representation of the physics. And so that's kind of what we did in here, both for time-dependent problems and boundary value problems. And I'll stop there. Thank you.
Thanks very much, Nathan. As always, great talk, perceptive, insightful, all of that. We can get questions started here, and I should just remind everybody that you should find a little box saying literally ask Nathan a question here, please. And you should type your question in there. I will relay it to Nathan. I'll get us started off with actually a question from myself, chair's prerogative here. When one is doing, really complex problems, right? And suppose we're really looking at a problem where we know nothing. I don't know, something in quantum mechanics to do with determining exchange correlation functionals whose forms are really not known, right? There's some idea, but not real. All right, so we start with maybe we have operators, integral differential operators, and so on. And now we start, and we do something like this, right? We have exactly this, right? We have a latent space. You worry about convergence, right? So you want, and mathematically now, you want your latent space also to be complete. Because then you have control over it, right? You have systematic convergence, you know that you attain limit, all that stuff, right? How does one think about that problem down at the latent space, right? How does one unpackage that, or is that still in the future? Yeah, something.
Yeah, it's a great question. I think, in some sense, one criticism I can level at myself, or others can too, which is if you notice what we've done so far, in some sense, we're still kind of like almost at this proof of concept step, right? Which is, sure, can I do some of these things? And I think part of what you're asking is actually kind of what I think is one of the most exciting pieces to come next, which is how well does this hold up when we go to much more complex problems? Because so far, the one thing I'm hopeful of is so far we've been able to find, as you go down this process, there are barriers, but you can get over them. It's not like, here's the barrier in which, mathematically, it's just like the undoable, right? For each barrier that's appeared, there's sort of ways to kind of get through it and around it. Like, for instance, the noise issue, that's one of the number one things you have to take care of first, right? I got measurement noise. How much of the physics can I actually see through that? And so I think we're now at the point that I think we're going to be able to start getting down to these problems and really addressing how complicated is this? I mean, I think we're still relying here on this concept of the dominant balance, right? So the only way this works is if, so for instance, let me back up. So if you have a problem like turbulence, I think it's very difficult for this to handle, right? It's not clear because, we still haven't figured out how do you do this cascade, right? You don't have clear scale separation. Where I think we'll be able to start making progress is in systems that at least if you have clear scale separation, I think we can do those. So I would say that's kind of where I think we will be able to work, is in problems where there will be a set of problems we'll be able to take steps in originally. And again, it may be just like today, we'll leave turbulence and we'll still be there 100 years from now, and it'll still be a problem for us.
Like the past 100 years, right? So
exactly.
Right. Okay, a couple of questions from the audience so far. The first one is from Timothy Thompson. Thanks, of course, for the great talk. Been trying to use the Koopman forecast algorithm to decompose and forecast signals from experiments. How does one conclude whether one's results are truly capturing the underlying and unknown dynamics, or have we given it too much capacity, right? Overfitting the data, essentially curve fitting.
So this is a great question. Part of it, because when you really get to real data, sometimes there's this fundamental question that I always think about with real data, which is the stuff I'm seeing in there, is that noise or some actual physics process that it's on fine scales, right? So one way to handle that, maybe as a suggestion, I'm not going to say it's going to work, but it's a good way to try it, is what we started doing recently is ensembling these Koopman models. So what you would say is, let me do this Koopman fit, but instead of taking, let's say if I have M snapshots of the data, I might take, P out of the data and then shuffle trial these. So by ensembling them, what it does two things. One is now you can average your models and see, okay, on average, what's actually persisting. In fact, I just put up a paper for DMD on this called BOP DMD, bagging optimized DMD. So the bagging thing is, so what your question really reflects a little bit is what people have known in statistics a long time, right? So they do this bagging trick where you just build an ensemble of models by just keep building the model, but with different random selections of the data and then average it out. And that always seems to work better. It doesn't necessarily mean you solved it, but at least you're going to make progress forward. And my hope is it would help take care of some of the it also takes care of oftentimes overfitting as well. So that's maybe something to try.
Great, thanks. The next question from Mikhail Poluektov. Great talk, fascinating talks, thanks. Curious about your opinion on classical models. It's a long history of modeling dynamical systems using classical black box models. Example, Hammerstein or Wiener processes. Some of these modeling and identification systems attempts were very successful. Do you think these approaches have any future, or the field will mostly be taken over by neural networks plus physics? So what's the future for Hammerstein and Wiener?
Actually, I think, ultimately, the one thing I just want to throw out again is, I just gave you an opinion of some things that I'm doing and I like and I think will have a future, but I think all of it's going to stick around. I think at the end of the day, it's whatever works, right? Look, we all like to explain what we do, but the fact is that some of these models stick around because they just work better than others. So, even in some of the original, I think, machine learning, as we're backing out the interpretations, right? If it works and it gives you a much higher performance score, of course you're going to use it. And you might worry about well, why does it work later? So I think all the methods we have, there might be some kind of nice convergence down the road about how all they fit together. But I think we're so early on that I think all of it's going to survive. I think we're going to survive with just straight scientific computing governing equations, right? Monte Carlo simulations, building, trying to build models by hand of discrepancies. We're going to have physics informed models. We're going to have deep neural net physics informed, and we're just going to have black box like this. I think they're all going to survive. I think they're all going to be important, and it's all going to depend upon which application regime, right? So you're going to use the one that does best, because the nature, we haven't even talked about the nature of data. I mean, that's one of the biggest things that we don't talk about. Here's these methods, but really, I always think the first question you ask is, well, what's the nature of my data and what's my goal? Am I trying to control the system? Am I trying to just classify data? Am I trying to do a forecast? So depending upon your goal and the kind of application, it will determine ultimately what method you use.
Great. Sort of, at the early part of your talk, I suddenly started thinking about something. So we've seen these papers where they've addressed essentially the planetary motion problem, right? So they've taken this data and said, okay, can we go from a geocentric to a heliocentric system? And there are papers which essentially unpackage their encoder architecture and showed that, yes, in the latent space, it is picking up the heliocentric structure. Great. Do you know of anybody trying to do this with the other big paradoxes that emerged? I mean, black body radiation, so are they rediscovering quantum mechanics or again, relativity, the next step also, right? Relativity,
no, we would love to sort of go down this direction. I think the hardest part is just actually getting the data. It's so hard because really at the end of the day, some of this, where you make progress is, so if you look here in a lot of our examples, they're synthetic data sets, right? Like I can run this thing that can easily make as much data as I want, and it's pretty cheap to run, like Shibashinsky, just run lots of batches. Versus when you go to real data, it's like, wow, how am I going to get it? How am I going to clean it up? Like even the planetary motion, you can look back at the original data set that Kepler had from Brahe, and it's interesting. It's exactly what we always think about, like, oh, here's a batch of data, and all of a sudden 3 months it's missing, right? And of course, you know, he went on a trip back to the court, and then he came back, or there's just missing nights, right? Because they couldn't see through, it was cloudy and rainy. So it's just like, it's the worst case scenario. It's not like what we always think about data. Here, I measured everything on a clock. It's like, okay, there's just massive gaps. And so trying to build the model with that data is hard. And what you almost need to do is like, okay, could I work with NASA? Could they measure it from some unoccluded source where it's super clean, and then I can clean it up? And then, but that's also not easy to get either, right? You have to spend a bit of time to really get that in place. But we would love to do that, where if you had some really clean planetary data, could you, from the data itself, not only discover the coordinates and the motion, but could you also say, and by the way, some of these planets, you can clearly see GR. In fact, you could have discovered GR directly through this kind of process, right? So, you know, that's the goal. Maybe one day we'll have the data to try it. So.
Cool. Fantastic, Nathan. You and I know, and everybody knows, we could all go on for much, much longer with this, but unfortunately there are, you know, things to do and conferences to wrap up here. So once again, thanks very much. Always great, and looking forward to much more. Thanks to everybody. You all know where to find Nathan if you have more questions.
Thanks, you guys. Have a great rest of the day, and thank you for having me, Krishna.
Great. Thanks, Nathan.